Good morning, students. So this is the next lecture, and we will start chapter 4. The title of chapter 4, Force System Resultants. All right, so we are done with chapter 1, chapter 2, and chapter 3. So we are done with 3 chapters, right? And today we are starting with the 4th chapter. Okay. All right, so force system resultants, we know that this is statics course, and we talk about force, we talk about equilibrium, right? So in this chapter, let's see what we are going to discuss. Okay, section 4.1, moment of a force, scalar formulation. Okay, so earlier in the earlier chapters we were talking about force, right? But now we'll talk about moment. So what is the difference between force and moment? Okay, so just take a minute and just think about it. Just think, what is a force and what is a moment, right? Okay, so let's look at this picture. So this guy is pulling this wrench with some force, right? So what is he doing? What is this guy doing? He's applying some force, right? He's pulling or pushing this wrench with some force. Okay, so that is the application of force. But what is moment? Now he is loosening up or tightening up this bolt with the help of this wrench, right, by applying some force. So what's going on here at the bolt? There's some rotation going on, right? There's some rotation, maybe clockwise, maybe counterclockwise, but there's some rotation. Okay, here, right here. So there's some rotation. Okay, so whenever we talk about rotation, we talk about moment. Or we can say whenever we talk about moment, we have rotation, right? So now this force is creating some moment at that point, right? At the point of the bolt. So that's how we relate force and moment. So now the important thing is that once the force is applied at some distance to the point of interest, right, then it creates some moment at that point of interest. In this case, in this figure, in this picture, we can say that this guy is applying force at this point, right? So now it's creating some moment at this point, right? Why? Because there's a distance between the point of application of the force and the point of interest, right? So that's how this force is creating some moment. Okay, so hopefully we are clear now about when does a force creates moment, right? Okay, all right, let's move forward. Applications of this concept once we talk about moments. So I think everybody has seen this going on. Once you use a hammer to pull a nail, right? To pull out a nail. So what sort of action does the force at the handle pull the nail, right? So this is the force being applied at this point, right? So this is the force being applied by this guy at this point, right? On the hammer. Now, what is this force doing? This force is pulling out this nail. Let's say we have a nail here, right? This nail. So this hammer is taking out this nail, is pulling out this nail, right? With that force Fh. But this hammer is rotating is at this point, right? So this force Fh is creating some moment at this point, let's say point A, right? So this force Fh is creating some moment at point A, and due to that, it's pulling out that nail. Okay, So that's how you can relate force, moment, and this is one of the applications. There are so many applications, right? Okay, let's move forward. Okay, moment of force, scalar formulation. Okay, so whenever we talk about static analysis, we talk about scalar analysis, we talk about vector analysis. Normally, usually we do scalar analysis in 2D system, right? 2D space, two-dimensional problems. Okay, and we do vector formulation for 3D system, 3D problems, right? Okay, so let's talk about moment of force, scalar formulation. Okay. All right, so let's talk some more. Let's look at some more things about moment. Okay, now this figure explains clearly that this guy is applying some force F at this point, right, on this range. Now this distance D is between the point of application of the force to the point of interest. Now point of interest is point O, right? Point O is point of interest, where this guy is loosening or tightening this bolt, right? Okay, so now again, as we discussed earlier, once the force is being applied at some distance from the point of interest, then it creates some moment, right? Some rotation. Okay, so this is that rotation. This is that rotation, right? This is the rotation going on due to this force. Okay, so we can say that there is some moment. All right, so let's see what's written here. The moment of a force about a point provides a measure of the tendency of rotation. Okay, so we already discussed about that moment and rotation are interconnected, right? They almost mean the same thing. Okay, all right, let's move forward. Okay, let's come here. So in a two-dimensional case, the magnitude of the moment, let's say M sub O is this guy, but why this guy? So let's say that we have a force F being applied, right? Let's say at this point, right? Now there's a point here, let's say point O. Now this is point O is the point of interest, right? Now we want to find out, we want to determine what is the moment of this force at point O, right? So we'll say M sub O, right? M sub O is the moment at point O. Okay. Now what is the magnitude of M sub O? It equals force F, which is this force, right, times D. What is D? D is this distance. Distance between the point of interest and point of application of the force, right? But one thing we need to make sure, we need to remember that D is the perpendicular distance between these 2 points. So it cannot be any other distance. It has to be a perpendicular distance between these 2 points, point of application of the force and the point of interest, right? So we need to find out, if not given, the perpendicular distance in order to find the moment. Okay, that's how you find moment. M sub O equals F times D, force times the distance D, and we call this distance the moment arm. Okay, so this D is called moment arm. Moment arm. Okay, so we need to remember these terminologies. All right, as we discussed, D is the perpendicular distance from point O to the line of action of the force. We already talked about this, right? Now in two-dimensional, the direction of M naught or M sub O is either clockwise or counterclockwise, right? Because once it's the force is creating some rotation, then the rotation will be can be in any of the 2 directions, clockwise or counterclockwise, right? So that's the direction of the moment, clockwise or counterclockwise. All right. Okay, let's move forward. All right, so let's see here. So this is the force F, being applied in this direction, right? As given by this blue arrow and these black dots. Okay, so this is the force F being applied. Okay, now this is point O. This is point O, which is the point of interest. Now we want to find out, we want to determine what is the moment at point O. Okay, all right, so now we know that as we discussed in the earlier slide, that m sub O equals F times d, right? Force times the moment arm, the distance. Okay, now if you look at this figure, what can you make out? Now this force is being applied at some distance d, right, from this point O. But if you look at the tendency of rotation, so this force is creating counterclockwise moment, right? Something like this at this point O, right? Okay, so that's how you can determine the tendency of rotation or the direction of rotation. Okay, so direction of rotation is counterclockwise in this case, right? Okay, let's see some more. Okay, now in order to find the magnitude of this guy m sub O, you need to have this guy d, right? Mostly the force is given, right? Force is already given, 20 pounds, 100 pounds, 500 pounds, any magnitude, right? But usually, sometimes the distance is given, the perpendicular distance between the line of action of the force and the point of interest, right? So sometimes this d is given, but sometimes d is not given, right? So once d is not given, and if you have these distances, let's say distance A and distance B, right? This guy and this guy. Then what you can do, you can resolve this force F into two components, x component and y component, right? And then you can find out m sub O by taking out the moments of these two components and add them up, right? So let's say same thing is going on here. So this was force F. First we resolve this force F into F sub x and F sub y, the x and y components of force F. Now we want to find out the moment at point O, right? So m sub O. Now how do you find m sub O? M sub O, we need to add the moments of F sub x and F sub y, Fx and Fy, right? X and y components. Now, this is the equation which gives us the moment at point O, right? M sub O, Fy times A, because Fy is this force, right? This force, and this is the direction of the force. And what is the perpendicular distance between the two directions, right? This guy, which is A, right? So Fy times A, which is this guy. This is the moment of Fy at point O. Now, if you talk about Fx, so this is the direction of the force, Fx, right? This is the direction of the force. What is the perpendicular distance? From this point to this point, what is the perpendicular distance? The distance is b, right? So what would be the moment? Fx times b, right? So this guy, Fx times b. But we need to cater for the direction of these moments, right? So for that, we use the sign convention for this two-dimensional case, and we take counterclockwise as positive and clockwise moments as negative, right? So now if you look here again, now this Fy is creating counterclockwise moment, right? So that's a positive. So we have a positive sign here, Fy times A. Now, if you look at this Fx, right? So Fx is creating clockwise moment, right? So Fx times A would be negative, right? So we have a negative sign here. So that's how you can determine the moment with the help of x and y components, right? So if you do not have the distance d, which is the moment arm of the force F, then you can find out these two components. And if you have these distances a and b for fx and fy, you can find out the moment from there. Okay. All right. So that's how you do it with the help of components. Let's move forward. Okay. Let's do one example. Right. If you look in this at this figure, there's a force of 100 newtons, right? So this is 100 newtons force, triangle ratio is given, and this is some kind of a structural member, 2 meters and 5 meters, and this is 0.0, right? This is 0.0, this guy, this is 0.0, okay? So what is given, 100 Newton force is applied to the frame, okay? What do we need to determine? The moment of force at 0.0, okay? The moment of force at 0.0. All right, so how we are going to do this? Now, first thing, we need to have the distance, right, between this guy, the direction of the force, right, and this guy, 0.0. Now, what is the perpendicular distance? It's this guy, right? You can say this is the distance d, which is the moment arm of this force at 0.0, right, the perpendicular distance. But in fact, we don't have this distance. As we discussed earlier, right, if we don't have this distance, then what do we do? So now, we are given this distance, right? So let's convert this, let's resolve this force into two components, x component and y component, okay? And let's see, what can we find out the moment from there? Let's see. Okay, so if we resolve this force into two components, right? So this will be Fy, and this will be Fx, right? So Fy and Fx. Now, just find out the moments from there for Fy and Fx. And if you look here, now this 5 meters is the moment arm for Fy. This 2 meters is the moment arm for Fx, right? Because this is the line of action of F sub x, right? And this is 0.0. So what is the perpendicular distance? This is the perpendicular distance, right? Between the point of interest, which is 0.0, and Fx. So 2 meters is the moment arm for Fx. Similarly, for Fy, this is the line of action of the force. So what is the perpendicular distance? This is the perpendicular distance for Fy. So 5 meters is already given, right? So we do have the moment arms for Fx and Fy, so we can just use the formula and find out these, okay? So let's first find out Fy, right? So Fy is 100 times 3 by 5 newtons, and Fx is 100 times 4 by 5 newtons, okay? All right, so that's how we find Fy and Fx. Now, let's find out moment, okay? Now, let's find out moment here, m sub o, we are taking moments at 0.0, and this is the sign convention. This is the sign convention which we use for finding out, for determining the moments, right? Counterclockwise, positive. It's very important that you use the sign convention and be consistent, okay? You can use clockwise positive, but most books and most people use counterclockwise positive, but whatever sign convention you use, you have to be consistent, okay? All right, so now if you look again at the figure, now this force Fy, this is creating clockwise moment, right? Clockwise moment. So Fy times 5 would be negative, right? So we have a negative sign here. We have 100 times 3 by 5, which is Fy, times 5 meter, which is the moment arc, right? Okay, so this is the moment due to Fy. Now, if you look at Fx, Fx is also creating clockwise moment, right? So that's why we have a negative Fx times moment arc. Okay, just use your calculators and you get a negative 460 Newton meters as your answer of this moment. Okay, Newton meter because it's force times distance. Okay, or we can also write 460 Newton meter clockwise. All right, so that's how you you write down moment. Okay. All right, so we are done with this example. Now, section 4.2, let's talk about vector cross product. Okay, so let's talk about vector cross product. We already discussed about vector scalar product, right? Mostly in 2 dimensions, sometime in 3 dimensions also, if the case is simple. So we do scalar product, but mostly in 2 dimensions. But vector cross product always in 3 dimensions, right? Once we have x, y, z, so you have 3 coordinate axes once we have 3 dimensions. Okay. Okay, let's talk about cross product of. Okay, here we are talking about vector cross product, right? So if you remember, we talked about the dot product earlier. Okay. We talked about the vector dot product in chapter 2, I think, or chapter 3 somewhere, right? So now we are talking about vector cross product. Okay, so cross product, once you have 2 vectors and you take cross product, then you get another vector. Okay, and this cross product we are going to use for vector formulation of moment. Okay, so that's the relation between vector cross product and the vector formulation of moment analysis. Okay, so once we have 2 vectors, let's say vector A and vector B, and you take a cross product, you get another vector, which is vector C. Okay, and you write it in this fashion: A cross B equals C, where A, B, and C all are vector quantities. Okay. And now writing it in this fashion will give you C equals A cross B. And how do you get C? You get A times B times sine of theta times U sub C. So we already know what is A, what is B. Theta is the angle between these 2 vectors. And what is U sub C? Because C is a vector quantity, right? So it has some magnitude and some direction. So what is this U sub C? This is a unit vector which gives us the direction of the vector C, right? So that's how you get the cross product of 2 vectors. Okay, let's move forward. Now we have another important thing which is called the right-hand rule, right? So right-hand rule is a useful tool for determining the direction of the vector resulting from a cross product. Okay. Now, if you look at this figure here, this shows the right-hand rule. Okay. Or if you go back, yeah, this picture also gives you, this figure gives you the right-hand rule, right? So if you take your right hand, so I want you to take your right hand and do it with me. Okay, so you have this vector A here, right, in this direction, and vector B in this direction. Now you are doing A cross B. So you are taking vector cross product of these 2 vectors A and B, and you are doing A cross B. Okay, so now you are going from vector A to vector B, right? So now you need to curl your fingers from the direction of vector A towards direction of vector B, right? So like as shown in this figure, just curl your fingers, right? Curl your fingers, and your fingers will curl from vector A towards vector B, right? Okay, if you do that, your thumb will point in the direction of vector C, right? As shown here, this is the direction of vector C, right? And this thumb is giving us the direction of vector C, right? And vector C is always perpendicular to vector A and vector B. So these are some details about the cross product, okay? All right, so let's come back here. Same thing here. If we have, let's talk about these direction vectors, right? I and J and K, okay? So this is vector I, x-axis, vector J, y-axis, vector K, z-axis. Now, if you again use your right-hand rule, right? Curl your fingers from I towards J, right? Because if you do I cross J, take the cross product of I and J, so you get I cross J, you get a K, right? Because K is perpendicular to I and J, and there's no magnitude because they are unit vectors, right? It just gives us the directions. So K equals I cross J, right? So you are curling your fingers from I towards J, and your thumb will point in the direction of Z axis, right? Which is your K direction, okay? And one more important thing, I cross I equals 0, right? I cross I equals 0, J cross J equals 0, K cross K equals 0, okay? Because you cannot curl your fingers, right? All right, okay, let's move forward. Now, I think every one of us has gone through these determinants and matrices, right? So we'll be using 3x3 matrix or 3x3 determinant to solve for the cross product, right? How we do that? So let's say we have two vectors, A and B, right? Vector A, vector B. So how do we get A cross B? The cross product between these two vectors, right? So we'll write down a 3x3 determinant, right? On the first row, we'll write down I, J, and K, right? The unit vectors giving us X, Y, Z directions. Then next row, second row, we'll write down the components of vector A, AX, AY, AZ. Third row, we'll write down the three components of vector B, so BX, BY, and BZ. Okay, so now we have a 3x3 determinant, and once we solve this determinant, right, so then we'll get the cross product between these two vectors. Okay, now I hope we all know how to expand this 3x3 determinant, or how to solve this 3x3 determinant, right? But let's go over it again. Okay, just to refresh your knowledge, let's go over it again. Okay, so we can expand or we can solve this determinant by making this into 2x2 determinants, right? Let's do that. Okay, so if you remember, again, it's just a refresher of your old knowledge. So you start from one side. So let's start with this row. Okay, so how we do it? We do it I times something, right? So once we take I, then this thing is gone, this thing is gone, right? As shown here. So you are taking this I, this thing is gone, this thing is gone, right? So we are left with this 2x2 determinant, right? So this guy AY times BZ minus AZ times BY, cross multiplication, okay, of 2x2 matrix. So that's how you get here I times AY times BZ minus AZ times BY, right? So that's what you get here, AY times bz minus az times by. Okay, so that's what you get here. All right, so that's about this guy I. Now for guy j, next component j would be, now we are taking this j, so this guy gone and this guy gone, right? So we are left with this, and this. This is not a negative sign, it's just an indication, right? So again, take the cross product, cross multiplication, ax times bz minus az times bx. So j times ax times bz minus az times bx. Okay, so we get this. Now, another important thing, remember this negative sign. This negative sign, right? Once you take this second component, right, or j component, you will put a negative sign. Okay, all right. Now let's come to the k component, right? So now we are taking this k component. This guy is gone. This guy is gone, right? So they're gone. So it will be k times this guy times this guy minus this guy times this guy. So ax times by minus ay times bx. Okay, so that's how you get this third component of this 3 by 3 determinant. Okay, all right, so just add them up and you get this cross product. Okay, all right, now let's move forward. All right, so section 4.3, moment of force vector formulation. As I said earlier, that we are going to use vector cross product in this vector formulation of moment. Okay, all right, so let's see here. Vector formulation, we are talking about 3D space. 3D space, we are talking about 3 dimensions, right? So x, y, and z, 3 coordinates. Okay, so let's see here. Now we have this x-axis, y-axis, z-axis. Okay, this is point O, let's say the origin, okay, or let's say point of interest. Okay, now this is force F. Force F being applied at some point in this 3D box. Okay, and O is our point of interest. Now we can resolve this force F into 3 components: Fx, Fy, Fz, along x, y, and z directions, right? Now we want to find out the moment at point O, right? So now we can find out moment of all these components, Fx, Fy, and Fz at point O, right? Okay. So using the vector cross product, how do we use the this cross product in our vector formulation of the moment? Like this, m sub O equals r cross f. So instead of going for Fx, Fy, and Fz, we are going for r cross f, right? What is r? R is the position vector. Where is r? This is r, right? Shown by this blue arrow. The position vector between point O and point of application of the force, right? Between this point and this point, this is the position vector. So if you just do r cross f, you'll get the moment in vector form, right? Okay. Now, I hope you remember how to find out how to determine this position vector. Okay. All right, let's move forward. Okay, so using the cross product, a moment can be expressed as this guy. M sub O equals r cross f. Position vector cross product with the force vector. Now, if you remember about cross product, how did we do that, right? So first row is ijk, right? The direction vectors, I, j, and k. Second row, in this case, is the position vector, right? So Rx, Ry, Rz. Okay, the three components of the position vector. Third row is the force vector Fx, Fy, Fz, right? The three components of force vector. Okay, so that's how you are going to do this. You are going to use this cross product, right, to find out the vector form of the moment. All right. Now again, the solution or solving this 3x3 determinant, we already did that, right? So let's not go into the details of that. How do you get this m sub o, right? Like this. This is the expansion of this 3x3 determinant. I times ryfz minus rzfy. And note that we have a negative sign for the second component, so second term of this 3x3 determinant. So negative j times rx times fz minus rz times fx plus k times rx times fy minus ry times fx, right? Just expand this 3x3 determinant and you'll get this equation to find out, to determine the moment in vector form. Okay. All right, so let's do another example on this moment formulation vector form. Okay, if you look at this picture, what's given here? There's some pipe assembly, right? Some kind of pipe assembly which is I think fixed at point O, right? There is this point A, two forces are being applied, F1 and F2. Okay, now F1, the vector form is given, so F1 is 100I minus 120J plus 75K pounds. F2 is given, negative 200I plus 250J plus 100K pounds. What do we need to find? We need to find the resultant moment by the forces about point O. Okay, so this is a 3D system. We have x-axis, y-axis, z-axis, right? So 3-dimension. And we have these two forces, and we have this point O, right? And we have these measurements given. Okay, so we need to find the resultant moment of these forces F1 and F2 about point O. Let's see how we are going to do it. Okay, so what are the steps? First, let's find out force F, which is F1 plus F2, because there are two forces, so we don't want to do the analysis twice. First, find out the moment with respect to F1, and then find out the moment due to F2, and then add them, add the two moments. Why to lengthen the process? Okay, so let's do the short one, and first find out the force F, which is F1 plus F2, right? And then find out the position vector, because we need the position vector to do the cross product. Okay, so then we will find out the cross product, and then we'll do this m sub o equals cross product ROA, cross product with the force vector, right? To find out the moment at point O due to these two forces. Okay, so let's do that. Okay, so first of all, find the resultant force vector F. Okay, so how do we find that? Luckily, both of these forces, F1 and F2, are given in Cartesian vector form with ijk, right? If you look here, so this F1 and F2 are given in Cartesian vector form, right? So just need to add them, just need to add the I, J, and K components, right? So F equals F1 plus F2. Everything is in vector form. So just add the I components, J components, and K components. If you just add I, J, and K components, you'll get your vector F, or the force vector, or the resultant force vector in Cartesian vector form. So this is your vector F, force vector F, which is the resultant force, right? So negative 100I plus 130J plus 175K. Okay. All right. So this is that's how we got the resultant force. Now we need to find out what is the position vector ROA. Okay. Position vector ROA. This guy. Now, if you remember what we used to do for the position vector. In this case, we are going from O towards A, right? So A is the tip, O is the tail, right? So what do we need to do? Subtract the components, right? Subtract the coordinates. So tip minus tail. So A minus O. AX minus OX. AY minus OY. AZ minus OZ. Okay? If you do that, we'll get this as our position vector. 4i plus 5j plus 3k, and of course we have the units feet. Okay. All right. So let's not go into the details of how to find the position vector because we have already done the homework and class problems during the lecture, and now we know how to find position vector. All right. Okay. So let's move forward. After we have this resulting force in vector form, and we have this position vector, we can find out the moment with the cross product. Okay, so this is your M naught. This is your 3×3 determinant. First row is ijk. Second row is the position vector. So we have 4, 5, and 3. So we have these 4, 5, and 3, the second row. Then third row is the force vector. So we have -100, +130, and +175, right? So we have this as our third row, -100, 130, 175. Okay. Now just expand this 3×3 determinant or solve this 3×3 determinant to find out the value of this M sub O, right? If you do that, like here, then you get this guy, which is the moment at point O in vector form, right? So 485I negative 1000J plus 1020 times K. And don't forget to write the units. In this case, we have force in pounds, we have distance in feet, so it's foot-pound. Okay? All right, so that's how you use this vector cross product to find out the vector form of moment. Okay? All right, let's do one more example on moment. Okay, so what is given here? A 20-pound force is applied to the hammer. We need to determine the moment of the force at point A. Where is point A? Here's point A. Look at this figure. Okay, this is point A. We want to find out the moment at point A. Or which force? This is the force of 20 pounds, right? Shown by this black arrow. This is your x-axis, this is your y-axis. So luckily we are in two-dimensional space, right? We have x and y, we don't have z. Okay, so life is simple. Okay, so we need to find out the moment of force at point A. Let's go through the steps. As this is a 2D problem, resolve the force along the handles x and y axis, right? So this is the x-axis and y-axis, and we'll find out fx and fy, because again, we do not have this distance. This is, let's say, this is the line of action of the force. This is point A. So what is the perpendicular distance? This guy, right? This is the perpendicular distance. Let's say distance d, right? That's what we call in the theory. So the perpendicular distance or the moment arm of force F with respect to point A. Now, just see, do we have this distance? Do we have the distance d given? No, right? So if you don't have distance d, you might have the distances for fx and fy, right? So if you do that, now this is your sub x, right? And this is your f sub y. Okay, if you resolve this force F into two components, you will get fx and fy. Now luckily, if you see, This 18 inches is the perpendicular distance between the line of action of Fx and point A, right? Because this is the perpendicular distance between Fx and point A, right? So which is given 18 inches. Now if you look at Fy, so this is the line of action of Fy, right? This is the line of action of Fy, and what is the perpendicular distance? This is the perpendicular distance between these two, point A and line of action of Fy. So luckily we already have this given as 5 inches. Okay, all right, so that's how we simplify this problem, and we resolve this force into two components. Okay, so let's resolve the force. Fy equals 20 times sine of 30 pounds. Fx 20 times cosine of 30 pounds. So this, we'll use this angle of 30 degrees. Okay, so once we are done with this, finding out Fy and Fx, then we'll find out the moment, right? So how do we find moment? We know that, right? We'll sum up the moments due to Fx and Fy, and we'll consider the positive and negative sign with respect to the sign convention, right? So we'll use this sign convention always counterclockwise as positive. We are finding out m sub a. Now let's talk about first the moment due to Fx, right? So this is your Fx, right? This is your Fx. Okay. All right. So Fx, and we are considering this point A, right? So Fx, what type of rotation? Clockwise rotation, right? So Fx is creating clockwise rotation. So that's why we'll put a negative sign according to our sign convention. 20 times cosine 30 pounds is the force F sub x times 18 inches, which is the moment arm. Now, if you look at Fy, this is your Fy, right? This is your Fy. Again, this is point A. So, what this Fy is doing? Let's see. Again, clockwise, right? Clockwise rotation at point O due to Fy. So we'll again have a positive sign, negative sign times Fy, which is 20 times sine of 30 times 5 inches, which is the moment arm for Fy at point O. Okay, just use your calculators and you'll be able to find out that we have a moment at point A with a magnitude of negative 361.7 pounds inches. Because the force is in pounds, distance is in inches. Okay, and we can also say that 361.7 pound inches clockwise. So either we use this negative sign or we write clockwise. We cannot write both. We cannot say 361 pound inches clockwise. That is not correct. So either we put negative sign or we put clockwise. Okay. All right. So we are done with this. Now, I think this is the last topic for today. Moment about an axis. So we talked about moment in general. We talked about moment scalar formulation. We talked about cross product, and then we talked about finding out the moment or moment analysis in vector form, right? Now we are talking about moment about an axis, because previously we were talking about moment at a point, point A, point O, point B, somewhere. Now let's talk about moment about an axis, right? Determining the moment of a force about an axis using scalar analysis and vector analysis. Okay, let's see. Okay, some more on this moment about an axis. Why do we need moment about an axis? All right. Let's look here in this figure. What is this guy doing? Applying some force, let's say a force P at this point, right? At this point in some direction as sorry, as shown by this black arrow. Okay. The point of interest is this point A, right? So this is a wrench handle, right? And he's using this wrench to again maybe tighten or loosen this bolt. Okay. Now the question is, does all of the moment created by this force act to turn the socket, turn the bolt? Yes or no? No, right? Because we know that this moment, because now we are in 3D space, so this moment has components, right? This force has components, right? Fx, Fy, Fz, moment has components, Mx, My, Mz, right? Because we are in 3D space. So not all the components are helping us to turn this bolt, right? So that's why we need moment about an axis, right? Let's say about any axis, right? So let's say about this axis. If you want to find out the moment about this axis, then we want to utilize this method. Okay. All right. So let's move forward. Let's talk about scalar analysis. Okay. Let's talk about scalar analysis first, because that's a simple one, right? So moment of a scalar force about point O, we already know that. We already talked about that. M sub O equals F times D sub O, right? D sub O is the perpendicular distance from the point to the force line of action. We already know the moment scalar formulation, right? We discussed about that. Now, let's look at this figure. Now, this guy is using force F at this point, right? Again, to loosen this bolt, right? This lug nut of this wheel. Okay. So we have this y-axis, we have this x-axis, we have this z-axis. All right. Now the moment about y-axis, right? About this axis, what would be the moment? The moment would be this guy. M sub y equals F sub z times D sub x. Why? Because we will take the z component of the force, so we'll take F sub z, right? F sub z times dx, because this is the so we are talking about this guy, right? We are talking about this moment, M sub y, right? So M sub y means, now this is the point, so this is the distance between y-axis and the point of application of the force. So this is your distance, the moment arm, but this is along the x-axis, so this is d sub x, right? And Fz is creating a moment around y-axis, right? So that's why you write M sub y equals F sub z times d sub x. Okay. But again, many times it is hard to find the force components and the moment arm, let's say dx in this case, this guy. We cannot find dx, right? So that's why we use vector analysis. Okay. Now let's talk about the vector analysis. Okay. Let's talk about vector analysis. Again, if you look at this figure, so this is force F being applied at this point A. Point of interest is this point O. Okay. We want to find out this M sub O. Okay. So if you don't have the distance, the perpendicular distance between, let's say, point A and point O, then what are we going to do? Okay, what are we going to do? We are going to use our position vector, or we are going to use vector analysis. Okay, so our goal is to find the moment of force F about the a-axis. Let's say this is our a-axis, A. Okay, first compute the moment of force F about any arbitrary point O that lies on the a-axis using the cross product. Okay, so this is your point O, which lies on that axis where we are finding out the moment, right? So this is your initial step. Once you will find out M sub O, right? So M sub O, we already know that, right? We have done that, R cross F. So the position vector between point O and point A, cross product with the force vector, right? So once we do that, then find the component of M sub O along the a-axis using the dot product, right? So one cross product and one dot product. So we need to do two products to find out this moment about an axis, right? How do we do that? M sub A equals U sub A dot product with M sub O. Okay, so once we do this dot product between U sub A, now what is U sub A? U sub A is the unit vector giving us the direction of this AA axis, okay, or the axis of interest. So we'll do the dot product between U sub A and M sub O, which we found in the initial step. Okay, so once we do this, then we get this M sub A, which is the moment about A axis, right? And which was the requirement. Now, instead of doing these two products, a cross product and a dot product, what we do triple scalar product, right? So we only do one step instead of two steps to find out this M sub A, right? So don't go the lengthier way. Don't do two products, cross product and dot product. Just do one product, which is a triple scalar product, right? So how we do that? So now we want to find out this M sub A, right, which is the moment about A axis, right? How we do that? This is the linear way. U sub A dot product with R cross F. So one cross product and one dot product. Okay, but we don't want to do that. So we do this. Again, 3 by 3 determinant. First row is the unit vector about point A. So UAX, UAY, UAZ, right? That's the first row. Second row is your position vector RX, RY, RZ. Third row is your force vector Fx, Fy, Fz, right? So now this is the triple scalar product. First row is the unit vector, second row is the position vector, third row is the force vector. Just expand this 3 by 3 determinant, just solve this 3 by 3 determinant, and you'll get the value of this guy, which is M sub A. Okay, isn't that easier? Isn't that simple? Yes, it is, right? Instead of doing two products, we just solve this 3 by 3 determinant and we'll get our required result. Okay, in this equation, UA represents the unit vector along the A axis. We know that R is the position vector from any point on the A axis to any point A on the line of action of the force. We know that already. F is the force vector. We know this. Okay. All right. So let's move forward. Let's do some example. Okay. So this problem, as you can see on the screen in this figure, we have a force F, which is 200 newtons, shown by this black arrow, right? being applied at this point A. So this guy is applying this force at point A. Again, he's using this sort of a tool, right, to we can say opening up this bolt, right, or turning this bolt. Okay, so what's given, a force is applied to the tool as shown. Okay, we already know that. We need to determine the magnitude of the moment of this force about x-axis. Okay, so we have x-axis, y-axis, z-axis. So this is a three-dimensional problem. Okay, we have 3D space. We have these angles given, angles of the force, which it makes with x, y, and z axis. All right, and we need to find the magnitude of the moment of this force about x-axis. Okay, so we don't need to find m sub a, right? We need to find m sub x. Okay, now let's see how we find m sub x. Okay, all right, so we need to find this guy. M sub x equals one dot product and one cross product, u dot r cross f, right? So, but instead of doing these two products, we'll do one triple scalar product. Okay, so we'll do one triple scalar product instead of doing these two products. All right, so what we do, first thing, we want to find out the force F in Cartesian form, because we just have this magnitude, right, 200 newtons. We cannot use this. We need to have the force vector or force in vector form, Cartesian vector form, in order to do the triple scalar product, right, because we are dealing with 3D system. Okay, so once we do that, then we need to find the unit vector. Unit vector, this guy, unit vector showing the direction of x-axis. Now, what is the unit vector which gives the direction of x-axis? It's just one I, right? Because we are just using the direction of x-axis. So y is 0, z is 0, right? So we only have one I, which gives us the direction of x-axis. Okay, so we already know the value of this unit vector u. Okay, then we need to find this guy, the position vector ROA. Okay, which is the position vector from point O to point A. Okay, so once we have these, then we can use triple scalar product to find out m sub x. Okay, let's move forward. Okay, we already know what is small u, right? It is one I, because we are taking this unit vector in the direction of x-axis. So it's one I. If it's, let's say, u sub y along y-axis, then it will be 1j, right? If it is u sub z in the direction of z-axis, then it will be 1k. Okay, so just remember this. Okay, next we need to find out ROA, the position vector between point O and point A. Okay, now again, tip to tail rule, tip minus tail rule. Here A is the tip, O is the tail, so A minus O. Okay, so you have the distances, so you can find out what is the position vector. It will be 0I plus 0.3J plus 0.25K. So this is your position vector. ROA, AX minus OX, AY minus OY, and AZ minus OZ. So 0I plus 0.3J plus 0.25K. And of course, we have this unit of meters, right? Because there's a unit of length should be here, right? So, and everything is given in meters. Okay. Then we need to find out this force F in vector form. Now, how do we find out this force vector in Cartesian form? Okay, so we just have this magnitude of 200 newtons for this force F. All right. So, but we also have these angles. Angle of 120 degrees with x-axis. This guy. Angle of 45 degrees with z-axis. This guy. Angle of 60 degrees with y-axis. This guy. Okay, so we can use these cosine of these angles to find out this force in Cartesian vector form, right? So we'll do 200 times cosine of 120i cosine of 60j plus cosine of 45k, right? X, Y, and Z directions, I, J, and K direction. Okay, and of course, Newton is the unit of force. So we get this as the force vector in Cartesian form. Negative 100i plus 100j plus 141.4k, and of course, Newton is the units. Okay, so now we have F, we have R, we have U. Okay, so now we can use triple scalar product, right? So if you do triple scalar product, first row is unit vector, so 1, 0, 0. Second row is the position vector, so we have 0, 0.3, and 0.25 right from here. 0, 0.3, 0.25. Okay. Third row is the force vector, so we have negative 100, positive 100, and positive 141.4. So that's what we have here. Negative 100, positive 100, 141.4. Okay, so we have this 3 by 3 determinant. Just expand or solve this 3 by 3 determinant and you'll get this. So this is the explanation of how we get this, and you get this answer. M sub x equals 17.4 Newton meters counterclockwise. All right, so either you can write positive 17.4 Newton meters, or you can say 17.4 Newton meters counterclockwise. Okay, so that's how you use this concept to find out moment about an axis. Okay, all right, so let's do another problem. Let's do another problem. Okay, all right, if you look in this figure, there's some kind of bracket with this force F, 30 Newton's force acting at this point. Okay, at this point, right? And we have this axis AA in some direction at some point, right? Now, let's see. What's given? The force of F of 30 newtons acts on this bracket. Alpha, beta, and gamma is given. What is alpha, beta, and gamma? If you look here, this is your x-axis, this is your y-axis, this is your z-axis, right? Now, alpha is with x-axis, right? This guy. Beta is with y-axis, this guy. And gamma is with z-axis, this guy. Okay? So alpha, beta, and gamma, the values are given with respect to x, y, and z axis respectively. All right. So we have force magnitude, we have alpha, beta, and gamma, so we can find out the force in Cartesian vector form, right? What else? What do we need to find? The moment of F about AA axis. All right. So AA axis. Now, what do we need? What do we need for this kind of problem? Same thing, triple scalar product. Triple scalar product, what do we need? We need small u, let's say u sub a. We need the position vector. Okay, what else? We need force vector in Cartesian form. Okay, so if we have these three, we can find out the m sub a, right? Okay. All right, so find u sub a, find ROA, find f in Cartesian form, and use this triple scalar product to find out m sub a. Okay? All right, so let's move forward. Now, this is your axis AA. This is your u sub a, the unit vector giving us the direction. Okay? So, if you see, this is your y-axis, right? This is your y-axis. So this is also in line with your y-axis. So what is your this u sub a, right? Once we are moving along the direction or parallel to the direction of y-axis, then we have unit vector or u sub a equals 1j or just a j. Okay, so k is 0, I is 0, and you'll just have a j for the unit vector. Okay, so we have this u sub a done. Now we need this guy, ROA, right? The position vector from this point, let's say point O to point A. Okay, so same thing, tip minus tail rule. Here A is the tip, O is the tail. So you have the distances given. Just remember that we are in 3D space. So if you use that, you'll get negative 0.1 I, positive 0.15 K, because J is already 0. Okay. All right. So now we have this unit vector. We have this position vector. Now we just need the force vector. We can use alpha, beta, and gamma and find out the force in Cartesian form. Okay. So 30 is the magnitude. So 30 newtons times cosine of 60 times I, because 60 degrees is the angle alpha with the x-axis, and 60 degrees with y-axis. So cosine of 60 degrees times j, and 45 degrees with z-axis. So cosine of 45 degrees times k, and overall newtons is the units. So this is the force vector in Cartesian form. 15I plus 15J plus 21.2K, and of course newtons. All right, so now we have everything what we need: the unit vector, the position vector, and the force vector. Okay, now we just need to do this triple scalar product. Okay, instead of a dot product and a cross product, we'll just do triple scalar product. So this is your top row or first row, which is the unit vector, this guy. Second row is your position vector, so this guy, ROA. Third row is your force vector, so this guy. Okay, you have 3 by 3 determinant, right? Just solve this, expand this 3 by 3 determinant, right? You only have one component because this is gone, so we only have this. Okay, so you'll get this by expanding this 3 by 3 determinant, and you get 4.37 Newton meters as the moment about a axis, right? And that's how you show this m sub a, right? In this fashion. So this is the moment about a axis due to this force F of 30 newtons. Okay, so 4.37 Newton meters, which is positive. So we can also write down 4.37 Newton meters counterclockwise. Okay. All right, so that's how we are done with this, and we are done with today's lecture. All right, so this was the first lecture of chapter 4, and hopefully in the next lecture we are going to complete chapter 4. Okay. All right. Thank you so much, and see you in the next lecture.